properties of fluids, 1 mark questions. First question. A fluid is said to be Newtonian fluid when shear stress is. For Newtonian fluid, shear stress applied, required, supplied, directly proportional to, why I used the word supplied, the pumping of the fluid, that only, right, is directly proportional to rate of deformation. The deformation is angular deformation. Rate of deformation is also called velocity gradient. It is also known as velocity gradient. So, shear stress directly proportional d theta by dt, or shear stress directly proportional to dV by dy. That means a fixed boundary on which a viscous fluid is kept. Let this layer considered and apply the force, shear force on shear area. This is shear area top or bottom. So touch with the top of the fluid, bottom of the layer, bottom of the plate. Suppose a plate is equal to shear stress, that causing the layer to layer, the relative velocities exhibit, relative velocities. So this is the V, this is the Y. If you take a small element here at certain distance, this is dy, the small element change in velocity dy. That gradient, the angle tan theta, dV by dy. So shear stress applied directly proportional to dV by dy. This is d theta by dt, rate of angular deformation. That also correct. For Newtonian fluid only, shear stress directly proportional to velocity gradient. Not all the fluids. Non-linear existence for the fluids such as pseudoplastic, dilatant fluid, wing harm fluid, any thexotropic fluids. Let us see, when time comes, then definitely I will touch that area. At present, shear stress directly proportional to velocity gradient. Perfectly correct A. Answer A is correct. Answer A is correct. A fluid is one which can be defined as a substance which is ready to deform indefinitely by an application of shear stress, whatever be the magnitude. Fluid is a matter which responds to the only shear stress, not tensile stress, not compressive stress, not any other bending stresses or any other complementary stresses. Only shear stress responses which definitely, which deform, which gets motion by application of shear irrespective of the amount of the magnitude of the force. So B is correct. Fluid is a substance which deform indefinitely under the action of shear stress, shear force. Okay, this is not the correct. Pressure is same in all directions, Pascal's law. Practically compressible, not only incompressible. It can be valid for compressible also. Okay, failed. So C failed, D failed. Let us focus on A. Has that same shear stress in all points? No. Shear stress varies. In the 5 flow, velocity profile parabolic. The shear stress varies linearly. Point to point shear stress varies. Not uniform, not remains constant every point. So this also wrong. So for this question, B is 100% correct. Definition of the fluid is covered. Dimensions of the surface tension. Just now we discussed surface tension, symbol sigma. By definition, normal force in the tensile form exerted by the free molecules at the free surface, normal to the surface, per unit length exposed, perimeter length exposed. This is force units Newton, length units, perimeter length meters. This can be written as according to Newton's second law of motion. Newton is F is equal to ma, na? That. This is the Newton, mass is kg. So, weight case g. If moving horizontally, it can be a. It can be a. Acceleration. So, acceleration meter per second square is always valid. Kg meter per second square divided by meter. After simplification, kg meter per second square meter cancelled. The balance fundamental dimensional quantity is this much. M to the power of 1, t to the power of minus 2. M to the power of 1, t to the power of minus 2. Answer D. Right. So easy to score mark. Repeated number of times. The kinematic viscosity of the air. The kinematic viscosity of the air at 20 degrees. So air, in such case, a student supposed to apply common sense. Supposed to apply common sense, not go for derivation or a lengthy formula. As we know, viscosity of the liquid decreases with increase in temperature. One statement. Second statement, viscosity of the gases increases with increase in temperature. What common sense here? What we have statement? Viscosity of a gas increases. Viscosity of the gas increases with increase in temperature. Increase in temperature. Air is a gas. Water is a liquid. In case of viscosity of the liquids, decreases with increase in temperature. So, kinematic viscosity inversely proportional to temperature. Just common sense. Right. Kinematic viscosity of the air at 20 degrees. Say X value. Same air at 70 degrees. A question mark. It is a gas, na, air. 20 degrees to 70 degrees. Temperature increase. Whatever the X value will increase. That means this value definitely more than X. More than X. So, this value given 1.6 into 10 to the power of minus 5. See now, this is wrong, this is wrong, this is wrong, this is wrong. This is correct. So, 10 to the power of minus 5 common terminology. 10 to the power of minus 5 is a common, it's a factor, decimals, 0.0005. So, at 20 degrees 1.6. At 70 degrees more than 1.6. 1.82, 1.6, 1.2. Wrong. If it is, suppose same value for the water, definitely answer C. because 1.2 is less than the 1.6. Na? Now, temperature at 70 degrees shall be more than the 3.2 10 to the power of minus 5. Answer D. This is the logic. There are some empirical formulas, there are some relationships, alpha, beta, temperatures and all. I am not taking that sense. Just a common sense, just observation of the type of the fluid. It is a gas, temperature increase, viscosity increase. If it is a liquid, temperature increase, viscosity decrease. That sense applied. Perfect answer is D. Newtonian fluid. Right? Newton's law of viscosity states that shear stress in the fluid is proportional to, as we discussed already, shear stress directly proportional to rate of deformation, rate of shear strain, right? So, velocity wrong, shear stress proportional to V wrong, time rate change of velocity, shear stress proportional to dV by dt. dV by dy correct. Shear stress proportional to square of the velocity, wrong. Rate of change of velocity with respect to height of the fluid, perfectly correct. Rate of change of velocity with respect to height of the liquid film, right? Right. This gap is dy. This is a dv, right? The change of velocity with respect to height of the fluid film change. Answer C correct. A good question. Answer C correct. A cubic block of side L and mass M, capital M, is dragged over an oil film. This is oil film. Across the table by string connected to a hanging block of mass M. Shown in the figure. Newtonian oil film thickness H has dynamic viscosity mu and flow conditions are laminar. Okay, layers parallel each other. Due to action due to gravity is G. Yes. Then what is the steady state velocity gained by the blocks? V. Assuming that solid friction, surfaces of the metals or whatever the surfaces of the table and whatever that air drag, everything neglected. There are some assumptions, right? So we need a free body diagram. If you go for a free body diagram, this is the fixed surface. Right? This is the block, right? And it is pulling with the force tension T. T is the tension in the string. Right? This is the mass M, moves with velocity V. And the gap is H, dynamic viscosity this. According to Newton's law of viscosity, Newton's law of viscosity, shear stress is equal to dynamic viscosity into velocity divided by gap H, right? Then shear force is equal to shear stress into area. The area is side L and L, na? Say block, cubic block, all sides are equal. So L into L area, right? So mu into V into H into area L into L. Then mu times L square into V by H. This is equation 1. We don't know pulling force here. The pulling force is T. This is called force parallel to surface. Force applied, force needed to drag to pull the block. M. Force needed. Then how to find force needed F? Go for the pulley arrangement. Okay, this is a pulley arrangement. This is the passing this. This is the mass small m. The weight is mg. And here tension T. If you take the free body diagram, for steady state, acceleration 0. Right? Sum of the forces in y direction is equal to m into a. The upward force is T, downward force is W, mass into acceleration 0, because acceleration 0, because steady state velocity remains same constant. Then T is equal to W. T is equal to W is equal to mg. Therefore, F is equal to T is equal to mg. Replace the tension in the string. Replace the tension in the string T is equal to F is equal to mg. Then substitute that. This is equation 2. Equation 2 is equal to equation 1, right? 1 is equal to otherwise. Equating 1 is equal to mu L square V by Y is equal to small m into G. Again cross check. Mu L square V by H. Mu L square V by H. Mu L square V by H. H is given, na? Use H. Steady state velocity V is equal to m g h divided by mu into L square. mgh by mu L square. mgh by mu L square. Answer C. Small m. Capital M is weight is acting in this direction, but motion is in this direction. Na? So mgh by mu L square. Answer C. Excellent question. Right, 1993. Shown below are 3 cylindrical gates. It is the front view, elevational view, not top view. Front view. That means this is projected like this. It is like this. Right? A cylinder of length L. 3 cylindrical gates which are restrained water in 2D channel. Yes, this is the water, right? These are all water. Right, like this. Right? Okay. Vertical axis, right? This, right. Which gate experience maximum vertical component, minimum vertical component, and maximum horizontal component of the hydrostatics? There are 3 cases. Let us see each case. Every curved surface wetted with liquid. Right. Here see. 3/4 of the circle, 3/4 portion of the cylinder touch with liquid, say water. But here, one side in contact with the restrained wall. This is the wall. Here you see, resting on the ground. Here also, 3/4 portion, 3/4 of the cylinder under wetted, but supporting at 2 points. So these are the restrained points. Na? Here 1 point restrained, here 2 points restrained. Here, a semicircle means minimum area, minimum volume in contact, right? So, every curved surface under wetted condition, every curved surface of the body under wetted condition subjected to 2 components. One is horizontal component of hydrostatic force. Second is vertical component of hydrostatic force. Horizontal hydrostatic force is equal to the projected plane vertically, that middle H bar, it is cylinder projected on the wall, rectangle shape, height diameter d by 2, right, H bar into area, whereas the vertical component is equal to weight of the fluid displaced by that body, weight of the fluid displaced, weight of the fluid displaced by body, by the contact surface. That means specific gravity of that fluid into whatever it is, a specific weight or mass density. Mass density of that fluid into acceleration due to gravity G into wetted volume. More wetted volume, more vertical force. Horizontal surface, only one side say water, other side no restraints. Definitely the reactions offered, the net force is less, right? So this is the how ideas. Now if you take horizontal force, here horizontal force, here horizontal force, here horizontal force, right? Now here horizontal force, here horizontal force more. The reason, the total amount of the force effect H is equal to rho G H bar, nothing but d by 2 into area L into d. Here this side no restraints, there is no resisting walls like that. Here there will be a reaction here. Here there will be reaction. Here also reaction. Here also reaction vertically. Here also reaction. Here more resistance. FH is there, that is opposing by the reaction of the wall. So net horizontal force is less. Net horizontal force is less. Here both the cases net horizontal force is equal less. Here net horizontal force is more. So with this explanation, first point, FH is maximum in C case. Horizontal force maximum in C case, because here no resistance offered like these. This is the resistance, it shares something amount. The net force is equal to FH minus this resisting force. Here also fluid touch, here also fluid touch. FH horizontal right side minus FH horizontal. Here also FH horizontal this side, FH. The net force is equal to FH right side minus FH left side, and net reaction is this only, FH minus F left is equal to reaction. In this case also, right side, left side horizontal component, right side 1/4, this side also component FH. The net force horizontal is less, both the cases are same in this, okay. But here only one FH, there is no opposing liquid here, no, there is no fluid here. Here fluid is there hatching, here fluid is there. This fluid right side, this fluid left side, net force is less. So maximum horizontal component is in case C, it has more. Now think about the vertical. Vertical force means the net wetted volume, maximum in which case? Net wetted volume maximum in which case? In this case maximum. Here total volume wetted more here. Here bottom touches na. So if you write this, first case horizontal component of hydrostatic force is maximum in case of C, because there is no opposing this side. Here wetted, this side. Here also wetted. So net force is difference of left side and right side. Here nothing is there, air only, is here liquid. So horizontal component of liquid more in case of 3. Yes, second. Vertical component of hydrostatic force is minimum in case of C only. See, less volume displaced. Here more volume displaced. Here only semicircle. Here triple, 3 circle. 3/4 of the circle. Here also 3/4 of the circle. The net force on the case 3 is minimum. Yes, minimum. So case 3, maximum horizontal component and minimum vertical component. Case 3. Now come to the, as per the examination, maximum vertical, minimum vertical, maximum horizontal. Maximum horizontal, right? Maximum horizontal case 3, minimum vertical case 3, then maximum vertical component target. Maximum vertical component. Vertical component of hydrostatic force is maximum in case of what? See here. Less wetted volume. When you come to here, see, more volume displaced. Here bottom also, here in contact. It seems to be same. But here bottom, here touch. The vertical reaction offer, separating, na? See here. Here more volume, so more buoyancy force in this case. So case A is correct. Case A is correct. Case A, maximum vertical component. Case C, minimum vertical component. Maximum horizontal component, case C. So C, case C reflecting. Case C reflecting to maximum horizontal component, minimum vertical component. Case 1 is maximum vertical component because more wetted volume, entire body, even bottom also a upthrust is there. Yes, a good question, conceptual question. Bodies in flotation is to be stable. Floating body stable, for which the necessary sufficient condition of the CG. Yes, a body floating in liquid. Now there are points. Capital B, center of buoyancy, where buoyancy force acts. Capital C, center of gravity of the whole body, where weight of the body. When it is tilted, theta, there will be a meta center M. GM is the metacentric height. If M is above the G, GM value is positive, then that is called stable floating. The center of gravity located below the metacenter. Answer is below the metacenter. Below the metacenter. below the metacenter. Which one? G. Center of gravity G located is to be below M. That is, metacenter M should be above the G, or GM value positive. GM value must be greater than 0. This is called stability of the floating body. So you have to write there, fill in the blank, below the metacenter. Metacenter is the answer. Here, metacenter word, if you write, then you will get marks. Fill in the blank, so many 20 years before, right? 25 years before, 1994, right? 22 years almost, right? Or 28 years, right? 28 years before this question. A mercury manometer is used to measure the static pressure at a point in the water. The level difference of the mercury of the two limbs 10 mm. Then what is the gauge pressure at that point? Here, this is the mercury manometer. This is something water. So now, this gap is 10 mm, this gap is 10 mm. Here height is not given. Ignore it. But when this is not given, you cannot assume anything, just ignore. Under that assumption, under that this is not known, then proceed. As we know, pressure at that point, say pressure at a point O plus this height, ignored because not given, and this height is equal to pressure at this point according to principle of manometer, or Pascal's law, hydrostatic law combination. Manometry principle says a reference line in such a way that at least one side same fluid exhibit. The pressure at X is equal to pressure at Y. Pressure at X unknown, nothing but PO. Plus this height is not given, ignore, but this height is given 10 na. Density of the water G into H water. Total pressure with reference to X above the reference line positive is taken, plus P0 plus rho WGH is equal to other side rho M G HM, right? This side, this is mercury, this is the mercury. Now resultant PO is equal to mass density of the manometric fluid into G into HM minus rho water G H water is given 13,600, 9.81 into 10 mm, 10 by 1000 meters, meter per second square, kg per metric, minus water 1000 G 9.81, and here height also same, 10 mm mercury, 10 mm water considered, so 0.01, this also same units. Now with this 13,600 minus 1000 common factors difference into 9.81 into 0.01. So this answer 1236 Newton per meter square. 1236 Newton per meter square. Answer A, Pascal. Right. A answer correct. A circular plate 1 meter in diameter is submerged vertically in water such a way that the circular plate upper edge is 8 meters below the free surface of water. What is the total hydrostatic pressure force on one side of the plate? Yes. This is a free surface of liquid. Here a plate is lying. This is circular plate. Right? This is the distance y. This is circular plate. This is the liquid. Right? This is the diameter d. As we know, hydrostatic force on the plate F working at center of pressure H star, but magnitude depending upon is center distance H bar. F is equal to hydrostatic force on vertically located circular plate on one side liquid. One side rho G H bar A. Standard formula. Average pressure into area. Is a vertical plane. This is equal to rho into G into y plus d by 2. Y plus d by 2 into circular area pi by 4 d square. By substituting these values, y distance given 8 meters, 1 meter diameter, 8 plus 1 by 2, area pi by 4 into 1 whole square. Into 8.5 into 9.81. 65.49 kilonewton. Exactly match. Answer B. $65.49 kilonewton. Interesting question this. The cross-section area of one limb of a U-tube manometer shown in the figure is made up of 500 times larger than the other. The cross-sectional area of the one limb of U-tube manometer made up of 500 times larger than the other, so that the pressure difference between the two limbs can be determined by measuring H on one limb of the manometer. What is the percentage error? Very interesting. Similar question also appeared in gate civil. Okay. So, just that changed. See, here pressure point. Due to pressure acting on the larger one, here small amount of change in the depth of the liquid in the large tank. Volume of the large container tank is equal to 500 times volume of this tube, measuring tube. Right. Now, if we apply pressure difference between these two, here and here, pressure at one side is equal to rho G delta H plus H. This is the total height, na? Delta H plus H. So, this is the reference line, this is the Y, this is the X. Pressure at X is equal to pressure at Y. This is the hydrostatic law, Pascal's law and manometric principle. From this concept, area of the tank, small change in the height in the large tank. This is the area is equal to 500 times into this small area. So cross-section area given, na? Cross-section areas are given. Cross-section areas are given, not volume. Cross-section areas are given, right? Written C, not volume. Cross-section areas. Cross-section area large, cross-section area small. Okay. Volume remains same. Volume remains same. Conservation of this. So, volumes are, this is given by conservation of mass. What are the total mass remains same? Conservation of mass remains same. The area into change in height, that is a volume change. There should be also change in volume, na? Small area A, area is pipe, area of tube. This capital A is area of the tank. Then by doing this, right, into H, this one. This is small area into capital H, right? Therefore, delta H is equal to A by A into H. You can substitute there. You can substitute here. Rho into G into delta H replaced. A by A into H plus H is equal to rho into G into H into A by A plus 1. This is the correction factor. Rho into G into H into some correction factor, this. So this is total entire the concept. Very interesting. This is called micromanometer. Yes. Now what is asking? The pressure difference between the two limbs can be determined by the measuring on H. What is the percentage error? This is the error only. This is the error. Therefore, error is observed. Error is to be small a by capital A. That additional amount. Small a by capital A is 1 by 500. Percentage point of view, .2% error is observed because of the difference in the areas. 0.2% error. 0.2% error. See how they are diverting questions. Not normally textbooks available. You need to have basic knowledge about the conservation of mass, then hydrostatic law, then Pascal's principle and the principle of manometer. This pressure X is equal to Y. Pressure X is equal to pressure Y. This is called manometric principle, right? The pressure applied here, small delta H change here, here large H change. The delta H by H error. So, concept is capital A delta H volume, small a H this. So, delta H by H is error is equal to small a by A. Small a by A areas, small area. So, delta H by H is error in the measurement of height. So, is equal to 1 by 500 into 100, 1 by say 5, 0.2% converted, right? Yes, converted, 0.2, 1 by 5%. Force F needed to support the liquid density rho or D, density rho or D, and vessel on the top shown in the figure. Here say this is frictionless piston written of area A. Above the piston, what is the pressure head? Pressure P is equal to force by area. Here pressure is acting. The pressure P is equal to this depth, rho G, this total height is H, rho G H. Pressure on the piston, not pressure on the wall. If it is wall, then rho g small h. Pressure on the piston. Piston is located at certain depth, capital H. So P is rho g h is equal to F by A. Right? So rho is replaced by D. D, G, H, F by A. Therefore, F is equal to G, D, H into A. Answer B. So simple question. G, local axiomatic gravity. D, density of the fluid. H is the depth of the water above the piston. This is piston. A is area of the piston. Whatever it is, pi by 4 d square, like that. Refer to the figure. The absolute pressure of gas at A. This is the gas. Gas density is very low. The bulb in terms of mm of mercury. We know principle of manometry. Take the reference line. We already familiar. Best reference line is, correct reference line is DE. Because one side of the tube filled with mercury. The pressure at D is equal to pressure at E. DA is reference line. Take DE is a reference line. Pressure at D is equal to pressure of the gas, pressure at A gas plus density of the water into G into depth of the water above the D. 10 plus 5 is 15, 15 plus 2 17, 17 centimeters is equal to that side over pressure of the gas at A plus rho GH. So the total column 10 plus 5 plus 2 17 is equal to pressure at other side rho mercury. Here 2 centimeter is a mercury, written in mercury 13.6, okay, gram per ml. So nothing but 13,600 kg per meter cube. Gram is 1 by 1000 kg. Milliliter means 10 to the power of minus 3, right? So that is the way 10 to the power of minus 6. So 13,600 kg per meter cube. Rho G H mercury, this column plus this one is water because that one is same. Rho water G H water right side. This is left side. Both sides water. And above this, right? Here data missing. Here above this there is a pressure inside as for original question. The 760 mm of mercury. From the original question 760 mm is there. I am taking that. That plus here some pressure is there plus rho mercury. Otherwise you will not get the correct option for the given. Plus rho mercury G H mercury given there. Atmosphere pressure, right? Say this is atmosphere pressure head. By substituting these values, we can get the correct answer. Pressure at A unknown gas, density 1000, G 9.81, head of water 10 plus 5, 15, 15 to 17, 0.7 is equal to 13,600 into 9.81, height of the mercury 0.02 plus density of water 1000, 9.81, height of water 0.05 plus atmosphere pressure given, we know very well, 760 mm. Yes. Now, by using simplification, we can get the PA. By simplification, I'm taking directive values. By taking simplification, PA is equal to 102.88 into 10 to the power of 3 Newton per meter square. This is not the answer examiner expecting. Examiner expecting in terms of mercury. So pressure at A gas is equal to rho mercury G H mercury at A. That is gas. Gas pressure head. 102.88 into 10 to the power of 3. 13,600 into 9.81 into head of the gas at A in terms of mercury. Therefore, head of the gas at A in terms of mercury is equal to 102.88 into 10 cube whole divided by 13,600 into 9.81. The simplification, you will get the 0.771 meters of mercury Hg. That is equal to 771 mm of mercury. See how time, 2 marks, na? Definitely. So you cannot ignore such calculations possible. 771 mm of mercury correct. Yes. Answer A correct. Answer A correct. This is the way questions. In given figure, if the pressure of the gas in bulb A is 50 centimeters of mercury, vacuum, negative, vacuum, and atmospheric pressure is 76 centimeters of mercury, then height of the column in the tube H, right? We know principle of manometry. We have concept of principle of manometry. What it says here, you can take reference line here or imagine this also reference line like this. This is all same fluid here. Here X, Y. Pressure head at X is equal to pressure head at Y. Rho into G into Hx. Rho into G into Hx plus pressure at A. This is the basic step. This is the P. Pressure at A. Okay. Now, here nothing is there. Gauge pressure 0. Everywhere atmosphere. Atmosphere pressure is there. With reference to gauge pressure, 0 gauge pressure. At X 0 gauge pressure. At X 0 gauge pressure. Nothing is there, na? There. 0 is equal to rho mercury G, this capital H plus rho mercury G into H at A. So by simplification, this rho G, rho G, rho G, rho G cancel. 0 is equal to capital H plus HA. Therefore, capital H is equal to minus HA. The minus HA value given 50 centimeters of mercury. Whatever the pressure head in the tube, that is nothing but pressure in the bulb, negative pressure, 50 centimeter H, right? So 50 centimeter H vacuum, right? The H height is 50 centimeter. Already given na is minus there, negative. So minus minus plus. You can say 50 centimeters H reading. The reading shown by the that manometer, H, nothing but pressure at the A. Here may be gas, neglected density. So pressure head at A, nothing but capital H. The capital H is equal to H at A, simple, negative, okay, that is vacuum. So 50 centimeters height, vacuum representing pressure. So very interesting question. If at all question in terms of absolute, then we should consider the local atmosphere pressure. So streamlines, path lines and streak lines are virtually identical. Yes, in which? In steady flow. Yes. If you take an example, this is something, a L-shaped tube, okay, like this. It is kept in the fluid. Something, this is a liquid. Through this, pour some beads, okay, some dye, right, say like this. This is some fluid is poured, some color fluid, dye. Now, the fluid particles, selected 7-8 fluid particles. The first one releases particles 1, 2, 3, 4, 5, 6, 7. At a given instant of time, there are 7 particles in fluid media. Each particle tracing its own path is called path line. At a given point, if you draw a line, that is called streamline, parallel line, tangent line, whatever. If it's curved, then tangent line, normal lines, right? So tangent line is called streamline. At a given instant of time, join all the fluid particles at different locations. That line is called streak line. Path line is a loci of the fluid particle with lapse of time. Just you make a hutch like this. So from my mouth, split particles are coming. The split particles are spreading in air. Each split particle you can draw. These are path lines. Path lines can intersect each other, right? So streamlines are imaginary lines, tangent lines. So at given instant of time, if you join this path in steady flow, that properties do not change with respect to time. This is called path line. Every particle following same path. Marching soldiers in a queue. Then join these particles at a given instant time. Streak line. This can be a streamline, because imagine line. Once a path line is beyond our control. It is taking its own course. In steady flow, 7 particles here, joined that each particle same path line. Streak line is a human choice. You can join 7 particles at given instant time. Streak line and path line joined. Then streamline, you can draw according to your, this is the path followed, and that path, a straight line, again the straight line become tangent line. So hence, path line, streamline, streak lines are identical, same magnitude. In the steady flow only, not uniform flow. Yes, answer C. Explanation is given. In a flow field, the streamlines and equipotential lines are mutually perpendicular, orthogonally cut. Their slopes, streamline slope M1, equipotential slope line M2. The product of slope lines M1, M2 is equal to -1, except stagnation points. At stagnation point, 0 velocity, then no potential functions or stream functions are existence, right? So it is also important. In 2D, two-dimensional flow taken x direction, y direction, right? This is a streamline. Stream function line, streamline. Along the streamline, stream function constant or change of human 0. Then this one is potential line. The angle between them 90 degrees. This is the slope M1. This is the slope M2. This is the stagnation point. M1 into M2 is equal to -1. Orthogonally cut each other. Here also orthogonal. Here also orthogonal. But except stagnation point. That word is important. Answer D. Streamlines are parallel, right? Cut any angle, wrong. Then orthogonally everywhere correct. But except stagnation point, perfectly matching. This is the stagnation point where velocities are 0, right? So answer D is correct. For a fluid element in 2-dimensional flow, that is XY plane taken, it undergoes, any fluid can move linearly, translation, by applying shear stress, deformation, and if it is viscous fluid, rotation. Is not mentioned whether real fluid or ideal fluid. If it is ideal fluid, okay, then non-viscous, definitely it will not say rotate, irrotational. Okay, nothing is mentioned, but minimum guarantee motions, linear and deformation. If it is a function which satisfies velocity potential, is called irrotation, is called non-viscous, is called ideal. Then no question of rotation. Na? Only transition, wrong. Only deformation, wrong. Translation, rotation. Rotation is wrong. Rotation not possible in case of irrotation flow. That is non-viscous flow. Neglected viscous flow. But guarantee translation, guarantee deformation. Because motion itself is needed shear stress. Na? Without shear force, without shear stress applied, no motion takes place. In case of irrotation flow, in case of non-viscous flow, how it is possible? Rotation not possible. So answer C correct. Translation, deformation, guarantee. Okay, need not be rotational flow. So in XY plane, these are pure max, right? So this is the particle, say plane A, B, C, D. By applying this, it can take place, it can deform like this. And it can also displaces forward like this. It can also displaces like this. So translation and deformation. This is a deformation and this is a translation. So in XY plane, guarantee motions, translation called linear and deformation. Rotation is a choice. Unless otherwise stated, no need to consider it. Minimum guarantee to. If it is a viscous fluid, rotation also possible. It is irrotational, not possible this, right? So very clear, translation and deformation guarantee, not rotation. Rotation is the condition applied. So answer C. Existence of velocity potential function. Definitely fluid is irrotational, non-viscous. These are pure mathematical proofs. Okay, we engineers different than say science and master science in physics. Okay, these are mathematical proofs by using differentiation and all. Okay, anyhow, velocity potential function existence. Pi is existence. That means flow must be irrotational. Velocity potential function is permitted. So fluid is irrotational, then that function satisfies velocity potential function. So velocity potential function existence means flow is irrotational. Right. Answer B. Flow is irrotational. Circulation is defined as line integral of tangential component of velocity about a closed contour. This is y-axis, this x-axis. A fluid particle with a tangential velocity, right? This is a sweeping like this. Circulation means capital gamma is equal to vorticity into area enveloped, area swept. So this is 2 times angular speed into area. So this is the closed contour. Closed contour. It must be closed. Then every tangent line integral will give the circulation. Circulation is the product of vorticity and area swept, circular area, right? So that vorticity is 2 times angular speed. The units meter square per second. Meter square per second. So closed contour. Yes. Circulation is the line integral of a tangent velocity v or v cos theta, v sin theta, whatever the component tangential line about the closed contour. This is the closed contour. Radian per second. Meter square. Radian is not a fundamental unit. Right. Right. A Newtonian fluid has the following velocity field. V vector is equal to x square y I cap 2x square y z j cap minus y z cube k cap. Find the rate of shear deformation with respect to y z. U given x square y. V given 2x y square z. W is equal to minus yz cube. Rate of shear strain, rate of shear deformation, rate of shear deformation with respect to yz means fluid in yz plane. Fluid in yz plane. This is a yz plane. Perpendicular to yz plane is x. So this is equal to 1 by 2 now dou w by dou y plus dou v by dou z. Just angular speed about x-axis is equal to 1 by 2 dou w by dou y minus dou v by dou z. The minus become plus. That's it. Then substitute. 1 by 2 dou w minus yz cube with respect to y plus dou 2xy square z with respect to z. That's it. Now 1 by 2 minus z cube plus 2xy square. This is the numerical value. Now substituting x is equal to minus 2, y is equal to 1, z is equal to 2. Yes. Epsilon yz is equal to 1 by 2 z value given 2 minus 2, 8. plus 2 into x value, y value square. X value minus 2, y value 1. X value minus 2, y value 1. The 2 square is substituted. 1 by 2 minus 8 minus 4 is equal to minus 12 by 2 is equal to minus 6 radian per second. Yes, answer A. Excellent question. Minus 6 units, radians per second. The stream function in two-dimensional flow is given. Psi is equal to x square minus y square. Find the magnitude of the velocity at that point 1 comma 1. That point 1 comma 1. X is equal to 1, y is equal to 1. First you find the velocity vector quantities u. U is called Vx. I cap plus V is equal to Vy j cap. V vector is equal to, how to find u? U is equal to dou psi by dou y I cap. V is equal to minus dou psi by dou x j cap. This is equal to dou psi by dou y minus 2y I cap minus dou psi by dou x 2x j cap. This is equal to minus 2 into 1 I cap minus 2 into 1 j cap minus 2 I cap minus 2 j cap. U is equal to minus 2 units meter per second. V is equal to this. Then value V is equal to under root of U square plus V square under root of minus 2 whole square minus 2 whole square under root of 8 is equal to 2 root 2 units meter per second. 2 root 2 correct. Answer B correct. Answer B correct. A velocity field is given as V vector is equal to 3x square y I cap minus 6xyz k cap, where x, y, z are in meters, V is in meter per second. Determine if is it representing incompressible flow, is it representing irrotation flow, is it steady flow or not? A good question. Now we know by comparing standard format, velocity component along x-axis u is equal to 3 x square y, 3x square y. V is equal to minus 6xyz. Now, let us check one by one. Check for the incompressible flow. Nothing but a continuity equation for two-dimensional, right? Study unstudy material, okay? So, the condition is dou u by dou x plus dou v by dou y. Check this. If it is 0, yes, it is continuity equation for incompressible flow. Dou u by dou x is equal to 6xy plus dou v by dou y minus 6 into x into 1 into z minus 6 x 1 z. So, not equal to 0. 3x square y, 6xy correct, right? Now, it is given k, not v. Interesting point here, very tricky question. It is not v, It is K given. Careful. K given. That means W given. So this must be W with respect to Z. With respect to Z. 2D X Z plane. Yes. So minus 6 X into Y into 1. See how the ignorance. So one should be cautious. Into X into Y into 1. So cancellation this 0. Yes. The given, see high and K given, na? Not J. Right. So right. Now it is correct. Yes. It representing incompressible flow because it is satisfied continuity equation of the X Z plane. The flow in XZ plane, not XY plane. U given, W given, XYZ minus. Now, check for the rotation or irrotation. Right. Second point. Let us check this. For irrotational flow in omega XZ, nothing but perpendicular plane, omega Y is equal to 1 by 2 dou U by dou Z minus, because minus that we know that technique, right? Dou W by dou X. Check this. Dou U by dou Z 0. Dou W by dou U by dou Z 0. Dou W by dou X is equal to minus YZ. So 3YZ not equal to 0. So failed. It is not irrotation. It is rotational flow. It is rotational flow, not irrotational. Rotational flow, not equal to 0. No? Rotational flow. This is wrong. Right. Let us check the steady flow or not. There is no time implicit. No? There is no time implicit. So, U and V are independent upon time. Third point. U and V are independent upon T. Hence, steady flow. So, given one option, satisfied continuity equation. Satisfied continuity equation. Second, flow is rotational, not irrotational. Third one is time is not implicit. Okay. So, steady flow. 1 and 3 statements correct. 1 and 3 statements correct. Option A is correct. Option A statement, given statement 1, given statement 3 correct. So, option A is correct. Option A is correct. Velocity components in X and Y directions given. Find the value of lambda. Find the value of the lambda. Lambda this. Find the value of lambda. This is the lambda. For the possible flow. Dou U by dou X plus dou V by dou Y is equal to 0. Right? Lambda XY cube minus X square Y plus XY square minus 3 by 4 y to the power of 4 with respect to y is equal to 0. Lambda y cube minus 2xy plus 2xy minus 4 cancel 3y cube is equal to 0. this and this cancel. Lambda y cube minus 3 lambda into y cube minus 3 times y cube is equal to 0. That implies lambda minus 3 into y cube is equal to 0. So y is not equal to 0, lambda minus 3 is equal to 0, lambda is equal to 3. Answer D. In a hand operated sprayer, figure shown below, the liquid from the container, this is container, liquid from the container rises to the top of the tube because of what? There are 3 different elements. One element is container, fixed. In the container, certain fluid is there, say water example. Into that water container, one tube is inserted. We don't know size of the tube. If it is less than 6 mm, then capillarity effect is considered. Glass tube less than 6 mm, possibility of capillarity. Then next one is called sprayer, like a doctor syringe type, in which inside piston is there. Piston motion is linear motion, reciprocating motion. Right. When you apply force on the piston, this is the force applied on the handle of the piston. Then piston moves forward with velocity v. Here water, suppose liquid, here gas. So what happens? Velocity is so high, this should be here. That's all, this should be here. This should be here. This mouse should be here. Okay, here you assume that figure is here. Okay, I'm writing, see. I'm writing the figure, see, like this. This is the tube. Consider this only, not that. Questions cut and paste. So that time shifted, right? This is the container, this. So this is the piston, right? Like this. A stream of air jet. According to Bernoulli's equation, P by rho g plus z plus v square by 2g is equal to constant. Now, suppose z is eliminated, z is neglected, then if suppose ignore it, then P by rho g plus v square by 2g is equal to constant. Constant. Suppose 10 meters plus 90 meters is equal to 100 meters. 100 constant energy, certain unit, right? 90, 10 plus 90, it can be 90 plus 10, it can be 40 plus 60, it can be 30 plus 70. That means one decrease, another increase. According to this concept, pressure head inversely proportional to velocity head. That means velocity head increased, pressure decreased. V square by 2g inversely proportional to P by rho g, or vice versa, right? Higher the velocity, lower the pressure in this. Here lower the pressure surrounded, then this will push up. Here atmosphere acting. This is atmosphere acting. So higher the velocity head, lower the pressure. Higher the velocity, lower the pressure. High the velocity, low the pressure. Simply. So due to which what happens? It is so high velocity head. High velocity head. there low pressure head. An atmosphere is more than the low pressure head. Then water will try to come out because it has a space for the pressure difference. Flow from the higher pressure to lower pressure. Option B correct. Due to high velocity of the air stream, low pressure is developed around that stream. Okay. Suppose a jet aeroplane or something, a high speed motorcycle fellow, let him travel just near to you. So when he is moving with 120-140 kilometers per hour, sometime you may feel that you will tends to move that side only. Even high speed train, you should not stand near that high speed train. Speed is so high, railway bogies, that high velocity of the railway bogies drag the amount of air surrounded it. When air is drawn along with the train, there will be low pressure zone. Then a person standing will be moved towards train only. We have seen in the WhatsApps also, accidents are taken place. A man standing on the platform pulled by the train due to this concept only. So, higher the velocity head, lower the pressure head. So, corresponding this discussion, you can guess this. Suction produced by the air jet. Low pressure. Then top end of the tube, causing water to flow. Hand operated liquid spray shown below. Liquid from the container rises. Yes, he said already rises. This liquid is rising due to suction created, negative pressure created. Perfect answer B. Let us focus on the statements. Shown below are 3 pipes, sections, uniform diameter sections, through which water flows as is shown. Options A to D below pertain to the direction of the net force on the pipe sections due to the flow of water. State which of the options indicate correct direction of force for the pipe 1, pipe 2, pipe 3. So, he has given 3 pipes, but options are 4. Something here. Okay, let us sometimes get nowadays. Say, see, there are 3 cases. So, options 4, right? Okay. Let us take one by one case. So, examiner expecting the force of the water on the pipe, the net force, of the water on the pipe section, force on the pipe due to flow of the fluid. Let us take one by one analysis. Okay, pipe 1. Pipe 1 is given like this. Like this. Like this. And picture the coordinates. So, this is the coordinates. Plus, this is minus, this also minus, this is x dash, this is y dash, this is plus, this is minus, this is minus, this is plus, minus. This is a coordinate system, right? We know familiarly, right? Now, this is the water flow. So, this is section 1, this is section 2. Right? Assume that the pipe is laid on the floor. Elevations Z1, Z2 are equal. Section 1 Z1 elevation, section 2 Z2 elevations are same. Then pressures also not given. So, exit pressure, inlet pressure same. No pressure differences, right? Entered into y direction, leaving with x direction. Entering into the y direction positive, leaving with the x direction positive. Now, let us see how the forces, right? If you take the forces, sum of the forces in x direction is equal to initial momentum minus final momentum, mass fluid same, minus V2x minus V1x. sum of the forces in x direction, no pressures, only force, dynamic force. This is called hydrodynamic force of the water. This is the water subjected to flow, which is lying on the floor. Fx is equal to m dot, we know very well, rho into q. Q is discharged through pipe. So V2x positive minus V2x, x direction, positive value, because towards east west point of view, north to south point of view, north plus south, like that. Okay, then V1x 0 at one section, only y direction, no x direction. Then simplification, this will give you m dot v fx. Similarly, Fy, sum of the forces in y direction is equal to m dot into v2y minus v1y. M dot into, what is the velocity in y direction at 2? Only x here. Only it has x, no y works. So 0. Then velocity of the flow at 1, purely positive, because upward na. This is the v, this is the v, right. Now simplification will give you minus m dot v. If you are taking this, if you are taking these cases, fx is positive, this is fx, then fy is negative, this is fy negative, this is origin. So this is the force, this is the resultant force. Resultant force Fr is equal to case 1, Fr1, fx square plus fy square. Magnitude is not going to change because fx square, fy square, but directions na, directions important. Now it is the forces. Okay, now this reaction acting in this direction, this is reaction. Okay, this is reaction, normal reaction, say reaction. This is external force, say external. The force of the water on the pipe, force of the water on the pipe, this one. This is the pipe offered this. This is water offered on the pipe. So case 1, 45 degrees, both positive, both negative. Wrong na? Pipe 1 is second coordinate, 45 degrees correct all the cases, negative and positive. So pipe 1 you can give B option, right? I don't know how the question is formed, somewhere shortage of information, right? So this is the analysis which I written, this is the analysis, this is the reaction force. Okay, force, this is the force of the water on the pipe. This Fr1 pipe, say Fr1 dash, equivalent force resultant of the water on the pipe. Clear? So analysis correct. Take the pipe 2 case. Pipe 2 entered from the east, leaving to the north, right? Case 2. Right. This is the way, right? See. This is pipe 2. Right. Right. This is the section 2. This is the section 1. So here V1 is equal to V. So V1x is equal to positive V. V1y is equal to 0. When come to this, V2x is 0. No x direction. Na? V2y is positive V. I written all. Right. Now write the equation. Sum of the forces x direction pipe 2 is equal to m dot into V2x minus V1x. M dot is mass flow rate. V2x is 0. That is only pure y na. We followed this na. Right. Minus V1x is positive V. This is equal to minus m dot V. Yes, equation 3. Forces in x direction, pipe 2. This is the pipe offered resistance, inertia force, right? That type. Say rate of momentum force. Second case, sum of the forces in y direction, pipe 2 is equal to m dot into V2y minus V1y is equal to m dot into, what is V2y? V2y positive V minus V1y 0. This is equal to plus m dot V. This is the fourth equation. The forces of the pipe on the water, second coordinate, the reaction will be in the fourth coordinate. According to the system, here fx2 and here fy. This is the resultant case. Then reaction, that means this one. This is 45 degrees because magnitudes are same, na? Magnitudes are same, 45 degrees only. Now, the hydrodynamic force of water on the pipe 2 is fourth coordinate. Yes. Let us take pipe 3 case. Pipe 3 case. Pipe 3. This is the pipe. Like this. The fluid entered here. The fluid living here. The coordinate system is like this. Right? So here, this is the 2 section. This is the 1 section. So V2x plus V, V2y 0. Come here, come to here. V1x 0, V1y negative V. Careful. Now, the forces offered by the fluid. Sum of the forces in x direction, pipe 3 is equal to m dot into V2x minus V1x. M dot is equal to V2x positive, V1x 0. Positive m dot V. Equation there 1, 2, 3, 4, here 5. Sum of the forces in y direction is equal to m dot into V2y minus V1y is equal to V2y 0 minus V1y minus V is equal to plus m dot V equation 3. Resultant force is same, Fx square, Fy square, 40 degrees. When you draw the graph in this, x, x bar, y, y bar, right. So this is first coordinate, definitely. This is also first coordinate. Now, this is the resultant force on the pipe 3, again 45 degrees. This is external force, Fr dash 3, again 45 degrees. It is in the third coordinate, right? So, force of the dynamic action of the water on the pipe 3, third coordinate. Reactions, right? It is in fourth coordinate. First one is second coordinate. So, here this is second coordinate. Let us see second pipe. Fourth coordinate. This is in fourth coordinate. Right. Then pipe 3 in third coordinate. Pipe 3 in third coordinate. Right. Very clear. Now, figure shown below 3 pipes. Sections shown, right? A to D. Options A to D below pertaining to the direction of the net force on the pipe due to water flow. Moving fluid water force on the pipe. Is this correct? State which of the following indicate correct direction of the force for the pipe 1, pipe 2. Pipe 1, second coordinate, x negative, y positive, right. Pipe 2, fourth coordinate, that means 45 degrees, fourth coordinate, x positive, y negative, x positive, y negative. Yes, this is the option C applicable. Then pipe 3, third coordinate, both are negative. Yes, this is the D. So, pipe 1, B option, pipe 2, C option, fourth coordinate, even here, right? Fourth coordinate, negative, na? Fourth coordinate, negative. So, this is D option, right? Pipe 3, third coordinate, this is also fourth coordinate, yes, correct, initially correct. Fourth coordinate, x positive, this is positive, this is positive. This is x, this is y. This is x dash, negative. This is y dash, negative. Fourth coordinate, x axis positive, y axis negative. C correct. Third coordinate, both D correct. Yes, this is how a question is solved. We have to match them. Pipe 1, option B. Pipe 2, option C. Pipe 3, option D. Correct. True or false statement? Bernoulli's equation can be applied between any 2 points on a streamline for rotation flow field. Yes, correct. See, there are certain assumptions we familiar already for the development of Bernoulli's energy equation of the fluids. Flow is steady, fluid is incompressible, fluid is non-viscous, flow along the streamline. Yes, flow along the streamline we can apply even though Fluid is rotational flow. Rotational flow is nothing but viscous fluid. Fluid rotating about one axis and moving. Bernoulli's equation applicable for two sections, 2 points in two different streamlines, but flow should be irrotational. Again I am repeating. This is true. For this explanation I am delivering. Flow along the streamline is assumption with the condition of that flow is rotational type. Bernoulli's equation applicable for points, sections at two different points and two different streamlines, but a condition must be irrotation. Right. Bernoulli's equation can be applied between 2 points. Say this is the streamline, this is the streamline, this is the streamline, like this, equidistances. This is the point 1, this is the point 2. This is the flow along the streamline. The fluid, say particle changing like this, right? The particle changing like this. Particle rotating, right? Say like this. Initial position. After some time, the particle here. After some time, the particle here. After some time, the particle here. That means what? Like this. This is rotational flow. Bernoulli's equation applicable between two different points 1 and 2. Yes. Provided rotational flow. Right. Now these are the streamlines. This is the point 1. This is the point 2. This is the point 1. This is the point 2. Right. Now applicable. Yes. Provided flow is irrotational. Irrotational flow means fluid particle does not rotate, just moving like this. Now also Bernoulli's equation applicable. So this is called irrotational flow. This is called irrotational flow. Different streamlines, points are different. Point on one streamline 1, point on another streamline 4. Now irrotation compulsory. Along the same line, Bernoulli's equation applicable between 2 points. P1 by rho g plus Z1 plus V1 square 2g is equal to P2 by rho g plus Z2 plus V2 square 2g. Provided rotation flow. So true is correct. In a venturi meter, the angle of the divergent section more than that of the convergent section. No? See, this is the axis of the pipe. This is inlet pipe. The pipe cut and attached with the throat, convergent section. Like this. So this is convergent. This is divergent. This is the angle. This is the angle. This angle theta c this angle theta d divergent. Effective angle, proper angle theta d in around 7 or 7 to 8 or 7, okay. In order to retard the fluid velocity, thereby increasing the pressure, we use that. When you come to this theta c, it will be around 15. It's all books around, say less than 20 to 15. That means what? Angle of the divergent is cone angle of the divergent is less than that of convergent. Angle of divergent section is more, wrong, less. So, false statement. This is the false is correct. The false is correct. Answer false. The reason behind the angles to avoid the flow separation, plus recover the pressure energy which lost here. Higher the velocity head, lower the pressure. The pressure is so low that below the vapor pressure cavitation occurs, flow separation occurs. To avoid the flow separation, length of the divergent portion. To avoid the flow separation, the length of the divergent portion more compared to convergent section. Right? So, length of the convergent section is less compared to divergent section. All these reasons for the flow separation avoidance. So, present statement, angle of divergent section is more than that of convergent section, wrong statement, false. Navier-Stokes equation represents the or based on the conservation of what? Energy, mass, pressure, momentum. Navier is one gentleman, Stokes is another gentleman. Both people different names. Navier-Stokes equation applied for real fluids. Navier-Stokes equation applicable to real fluids. Real fluid is viscous fluid. Viscous force is considered apart from the body force and pressure forces. But what is the base for this? What it conserve? What it conserve? Momentum, rate, Newton's second law of motion. According to Newton's second law of motion, sum of the forces is equal to mass into acceleration. This is equal to, just now done, rate of change of velocity, that mass by time. That is equal to m dot into dv or rho into q into, sometimes people writing delta v. Rate of change of momentum. So based on this, they developed the equations rho into dv by dt. We are done in the pressure gradient equation time. Rho g plus, right? Then dp by dx, that type. So Navier-Stokes equation consider body forces, pressure forces, as well viscous forces. So these forces, these energies are conserved. So what conserved this? In the form of momentum, rate of momentum. Euler's equation also based on this. Their force per unit volume, that whatever that. So now energy, Bernoulli's equation, mass continuity equation conservation, pressure nothing, then momentum correct. Navier-Stokes equation representing conservation of momentum with the presence of viscous force. Impulse momentum equation also conservation of momentum. In the conservation of momentum, for our impact of jet. Viscous force ignored. Here viscous force also considered. That is the only difference. Navier-Stokes equation in mind means applicable to real fluids. It considers the additional force apart from the body force and pressure force. A new force is viscous force considered. Right. Conservation of energy, Bernoulli's equation. Conservation of mass, continuity equation. No conservation of pressure. This is scalar quantity. It is at given point exerted by the static and dynamic fluid. They are not conserving, right? See, form of energy, one form of energy, okay? Then momentum, yes. Conservation of momentum leads to Euler's equation in absence of viscous force. In presence of viscous force, it leads to Navier-Stokes equation. This is the conservation of energy, Bernoulli's energy equation. Conservation of energy leads to Bernoulli's energy equation. Conservation of mass, continuity equation. Yes, this is the momentum conservation. Euler's equation, correct? Newton's second law, as well Navier-Stokes equation. Navier-Stokes equation. Answer D correct. 1987, which I written when I was in third year, qualified, right? A mercury manometer is attached to a section of the pipe shown. Mercury levels are indicated when there is no flow. Yes, there is no flow at present. Levels are say mercury. It is like a venturimeter type, but both are convergent only, not divergent. If you look in this way, this is convergent, this is divergent. In this way, it is convergent, it is divergent. Flow in this direction. Mercury levels are indicated when there is no flow. Yes, this is no flow, right? Through the pipe. When water starts flowing through pipe continuously at a constant rate in the direction arrow shown, what about the levels of the mercury at B? Fall or rise? Yes, very clear. Here, high velocity. This is the convergent portion, right? This is the throat. Fluid entered from velocity V1 into the 2. This is section 1, this is section 2. Definitely V2 greater than V1. Velocity head more, pressure head. P2 less than P1. Means pressure here low. That means, see how it can be. Pressure is low here. Then come to this section. Again pressure recovered. Again pressure recovered. Here come to this. V3 less than V2. P3 more than P2. Right. Like this. Compared to that, right? P3 is more than P2. That means P2 less than P3. Yes. Now, when P2 is less here, then P3 is more than P2. What happens? It goes up. P2 more than P3 more than P1. Pressure P3 here more than P2. Here P2 less than P1, right? So here this is happening. Mercury level at B rises. Mercury level at B rises and falls at A. Okay. What conclusion now? Mercury level at A falls. Mercury level at B rises. Yes. Just now you proved Bernoulli's equation application, right? So P3 more than P2, P2 less than P1, right? So A will push down, B rises. So over a period of time, the mercury level is like this. The red color is the final. The red color is the final. At A falls, at B rises. At B rises, rises correct, falls wrong. So B rises correct. This is answer. Mercury level at B is rises compared to A, right? So this level will come down. This level will fall down. This level is disappear. This is the final. Yes. Water flows through a pipe shown in the figure, right? Of diameter 0.3 meters. What would be the velocity V for the conditions shown? Specific gravity of the mercury manometer, we familiar 13.6, but specific gravity of the manometric fluid is 0.8. Here specific gravity of water is 1. Specific gravity of water is 1. Specific gravity of the say oil is 0.8. If the manometric fluid in the differential manometer less than the, if manometric liquid mass density less than the liquid in the main pipe, then differential head delta Hm is equal to, or fluid in the main fluid in the pipe is equal to, fluid in the pipe is equal to, manometric fluid Hm, manometric fluid reading, bracket, not Sm by Sf, 1 minus Sm by Sf. Then velocity of the fluid flow in the pipe is equal to coefficient of velocity into under root of 2g delta Hf. This is equal to under root of Cv not given, suppose 1. So not given 1. 2 into g into manometric fluid oil into 1 minus oil by water. Substitutions. Velocity of the fluid in the pipe is water is equal to under root of 2 into 9.81 into manometric fluid height is 0.3 into 1 minus 0.8 by 1. Simplification, 2 into 9.81 into 0.3 into 0.2 square root. Square root 1.177 is equal to 1.085. Say 1.1 also, no issue. 1.085 correct answer. Right. 1.085 meter is correct answer. This is how simplification. Here, if you try routine matter, you will get square root minus. That indicates that something wrong with you. That means something wrong with you means the specific gravity of the manometric fluid is less than the specific gravity of the main pipe fluid. This is one special variety problem. 2 marks. PYQ. A jet of water issues from the nozzle this is nozzle with velocity 20 meter per second and it impinges normally on a plate moving away from the jet at 10 meter per second. The cross-sectional area of the jet is 0.01 meter square. The density of water is 1000 kg per meter cube. Then what is the force developed? What is the force developed by the jet on the plate? Interesting case. It is based on impulse momentum equation. Sum of the forces is equal to, we familiar already, mass into acceleration, mass into change of velocity with respect to time. That is equal to mass by change of time into dv. This is m dot mass flow rate into change in velocity. M dot is equal to rho into q into delta v. This is standard equation from the impulse momentum chapter. Here question is it fixed control volume or is it moving control volume? Plate is moving. Plate is moving. That means moving control volume. This is moving control volume case. Jet also moving, plate also moving. Then jet also moving, plate also moving. Then you need to have relative velocity. Jet is moving with reference to moving plate u. Then here v minus u. Both plates are moving. Both velocities are moving. Both plates wrong. Jet velocity and plate velocity have different magnitudes, but moving in the same direction, negative. Say note, if opposite relative velocity Vr is equal to this way. Just not solving the question given. While solving the actual question, so my intention is to add more information so that if case changes and you can identify that case. Relative velocity depend upon the direction of the velocities. Both the velocities like velocity of jet and velocity of the plate moving in same direction, in the same sense, maybe towards say something right side or towards left side, whatever it is, then v minus u. The jet is coming from say west to east, then plate is moving from east to west, then definitely v minus u. So minus plus v plus u. In our case, both are moving in the same direction because plate moving away from the jet. Yes, now change this. When come to this, rho into area of the jet into relative velocity into relative velocity here, change of velocity. Right? Final velocity relative as 0, y direction moving, now hitting and leaving, jumping. So finally, rho into area of the jet into velocity square. That is equal to area of the jet into, in this case, v minus u whole square. This is equal to 1000 kg per meter cube. 1000 kg per meter cube. Area of the jet 0.01 meter square into velocity of the jet 20, velocity of the plate 10. 20 minus 10 whole square, meter per second whole square. After simplification, the answer is 100, yes, no doubt, 10 into 10 square, okay, 100, yes. This is 10, no? that is 10 square, 100, right? See, 0.01 correct, 100 correct, yes. So what I want to say here, 10 left over, there 10 left over. So 1000, na? Yes, answer A. 1000 kg meter cube cancelled, meter to the power 4, na? Meter per second square. This is equal to force of the jet on the moving plate is equal to 1000 Newton. Answer A. Kg meter per second square. Kg meter per second square is Newton. This is the answer. 1000 Newton. Answer A. Answer A. 1000 Newton correct. A fan in the duct. This is the duct. This is the duct. Good. A fan in the duct. This is duct. A fan in the duct shown below suck the air. Suck the air from ambient, this atmosphere. Ambient means nothing but atmosphere only. And expel it as a jet with velocity 1 meter per second to the ambient, to the atmosphere. Determine the gauge pressure at the point marked at A. What is the pressure at this point? What is the pressure at this point? Okay, nice. Take the density of air as 1. Density of the air is equal to 1 kg per meter cube. Interesting. The gauge pressure at A is equal to, by definition, energy possessed by the unit volume. The kinetic energy of the moving fluid per unit volume of that fluid. That is called gauge pressure dynamic. Gauge pressure dynamic is equal to kinetic energy of the moving fluid divided by volume of the fluid. This is a joule. Joule is called Newton meter. This is the meter cube. This step. This is equal to half mv square divided by volume. Then we know rho is equal to mass by volume. Half into rho into v square. Half into rho into v square. Kg per meter cube into meter per second whole square. That is equal to kg meter, right, square, right, we can say like that, meter by meter cube per second square. Units manipulation. Now, meter square second square, na? Kg meter per second square is called Newton. Newton meter by meter cube is equal to Newton per meter square. Half rho v square Newton per meter square balanced. Right? Then gauge pressure dynamic. At a point A is equal to half rho v square of into one value kg per meter cube into velocity. Velocity given 1, everything 1. 1 whole square meter per second whole square is equal to 0.5 Newton per meter square. Units are balanced. Already we proved this. Right. So, dynamic pressure at this point A is equal to, pressure at this point A is equal to 0.5 Newton per meter square. Yeah, proved here. Yes, correct. 0.5 is the answer. Answer is 0.5 Pascal. Right. Shown below 3 liquid tanks. Tank 1 just hole, no orifice tube, Extended orifice tube is called mouthpiece. Mouthpiece is a small tube connected to orifice. A tank made drill, make a hole drill, that is orifice. For the hole, insert the tube, that is called mouthpiece, extended length of the flow. Tank 1, no orifice tube. Tank 2, yes, mouthpiece, one extended. Tank 2, tank 3, same. Only thing is that this inserted here, just welded at the bottom. Here, inserted here. According to our knowledge, Bernoulli's equation, this is the streamline, this is the streamline, this is the streamline, this is the streamline, this is the streamline. Along this streamline, Bernoulli's equation applied or torsionally applied, this velocity is equal to, root 2 GH. Here velocity is equal to root 2 G H plus L. This is equal to root 2 G H plus L only. Nothing to do with this projected portion inside the, maybe coefficient of discharge varies, but velocity will not change. Na? Okay. So, Bernoulli's equation applied along the streamline. This is the clue here. Bernoulli's equation, energy equation, applicable along the streamline, that is here axis of the tube. Maybe final discharge may vary, right? But the velocity remains same. Velocity V1 tank 1 is equal to under root of 2GH. Velocity tank 2 under root of H plus L. Velocity in the tank 3 H plus L. This is how. So, no options given. Only you have to write this one. Okay. So, this is Bernoulli's equation case only. Right. So, additional difference is this, but it will not affect velocity. Maybe discharge affects. Maybe resistance more, maybe final discharge differs. That affecting in terms of CD. Right. Another interesting question. The discharge velocity at the pipe exit of the figure. Now, apply Bernoulli's equation. This is the one. Here, velocity V. This is the section 2. Now, right. So, this is the datum level, suppose. Our Bahubali is here. Right. P1 0, P2 0, right? P1 0, V1 also assumed to be 0, large tank, nothing is given. Z1 is equal to capital H. Then come to here, P2 0, Z2 is equal to, this gap is H minus H. If you know familiar with the Bernoulli's equation, very easy to say, net head. Apply Bernoulli's, I want to make it from the basics. Let the time 2-3 minutes more, don't worry. But learning losses is equal to P2 by rho g plus Z2 plus V2 square by 2g. By substituting this, 0 by rho g plus h, 0 square by 2g losses, P2 0 rho g, Z2 is equal to h minus h, velocity at exit unknown V2, right. By simplification, what are V2 or V1, right? Right. V2 also okay, no problem. Then H and H cancel. Then this becomes H. Therefore, V2 is equal to under root of 2 into G into H. This is the answer, small h. Small h. 2GH. Units, meters per second. So, 2GH small h. Answer B correct. Answer B correct. Right. Answer B correct. Right. Okay. Clear. Water flows through a vertical contraction from a pipe of diameter D. This is diameter pipe, to another pipe of diameter D by 2. Show in the figure. Flow velocity at inlet to the contraction 2 meter per second. Pressure 200. If height of the contraction is 2 meters, then pressure at the exit, suppose if you take a section 1 and 1, here pressure is P1, here mean velocity V1 given 2 meter per second, right. Target is, what is P2? Then 2 meters is Z2. We don't know what is velocity. Interesting case, right. So, right. This is the 1. This is the 2. Pressure 1 given. This is the flow. Pressure 1 given. Pressure 1 given 200 kilopascal. Pressure P2 question mark. Z2 given 2 meters. Z1 is 0. Then V1 given 2 meters per second. We don't know V2. Using continuity equation and Bernoulli's energy equation, this question can be solved. Continuity equation first. Q is equal to A1 V1 is equal to A2 V2. Pi by 4 D square V1 pi by 4 d by 2 whole square V2. By simplification, this V2 is equal to 4 times V1. V2 is equal to 4 times V1. V2 is equal to 4 times V1. This is the first step. Second step, Bernoulli's energy equation. Bernoulli's energy equation. P1 by rho g, Z1, V1 square by 2g is equal to P2 by rho g, Z2, V2 square by 2g. P1 is given 200. Kilo means 10 cube. Pascal means Newton per meter square. Then what is the fluid given? Fluid is given water. So you can take 1000. 1000. G 9.81. This is called specific weight. Newton per meter cube. Rho g is equal to gamma. Gamma is specific weight. Newton per meter cube. Rho is kg per meter cube. G meter per second square. Plus 0 plus 2 whole square by 2 into 9.81 is equal to P2 unknown into same 1000 into 9.81. 1000 into 9.81. Z2 is 2 meters. V2 calculated 4 times 4 into 2. Therefore, V2 is equal to 4 into 2 is equal to 8. 8 whole square by 2 into 9.81. By simplification, this P2, you will get kilopascal, kilonewton per meter square. Yes, 1000 cancel. 200, okay, right. 2 cancel. 2 divided by 9.81. 2 divided by 9.81 plus bracket 200 into 9.81 inverse, that minus 2 into 2, right, 18. So 18.5, okay, that is correct. So minus bracket 632, 32 into 9.8 inverse 1, this one, okay, yes, into 9.8, around 150, around 150, correct. I got it, 150, right. 150 kilopascal simplification. Here, accurately speaking, 150.3. Calculator 150.3. Here, very clearly showing 150.3. So, near answer 150. Correct. Answer C. Answer C. Right. Fully developed flow, laminar flow through pipe. Ratio of the maximum velocity to average velocity. V max by V mean or V average or V mean. Answer is 2. Okay. Let us focus how it can be. We know velocity at radial distance from the central axis is equal to 1 by 4 mu minus dp by dx r square minus r square. V max is equal to 1 by 4 mu minus dp by dx into r square. We know these two equations familiar. We want to prove this. We want to prove this, right? So, for which we will take the small element strip. These are the equations we know. Take a pipe, just I want to prove it in few minutes. This is the pipe. Flow is confirmed laminar. This is small strip like this. If you see like this is small strip. This is capital R, this is small r, right? So, this is dx, this is small r, this is capital R. We know this discharge through small this stream tube dq is equal to dA into VR, right? dq into dA means 2 pi r this ring into that strip thickness dr into VR. Now dq is equal to 2 pi r dr, VR is 1 by 4 mu minus dp by dx into r square minus r square. Now by integrating properly, dq integration 0 to q, 2 pi constant, 4 mu constant minus dp by dx constant, then integration properly multiply this r here, r square into r square into r cube into dr. Okay. Now by applying this 0 to r, by taking this q is equal to, by writing this pi divided by 2 mu minus dp by dx into integration of this r square into r square by 2, r to the power of 4 by r to the power of 4, limits 0 to r. Yes, q is equal to pi divided by 2 mu minus dp by dx into r to the power of 4 by 2, r to the power of 4 by 4, bracket close. Q is equal to pi divided by 2 pi minus dp by dx into r to the power of 4 by 4. Right. By taking this properly, right? So Q is area into average velocity is equal to do. A is pi r square, normal area or cross section pipe, into V bar is equal to pi divided by 2 pi dp by dx into r to the power of 4 by 4. By simplification this, so very clearly pi cancel, right? So properly r square cancel, r square times out of r. The balance terminology, V bar is equal to 1 by 8 mu, bracket close, minus dp by dx into r square. By taking this 1 by 2, 1 by 4 mu dp by dx into r square. By taking this logic, V bar is equal to 1 by 2 into, let us see, right, here step, V bar is equal to 1 by 2 into 1 by 4 mu minus dp by dx into r square. V bar is equal to 1 by 2 into V max. So therefore V max divided by V mean for a laminar pipe, laminar pipe only, not parallel flow, is equal to 2 times. Proved. Maybe 3 minutes, 2 minutes, but revision has been done. V max by V bar is equal to 2. Yes. Answer 2. Here you have to fill the 2. So given expressions, just simple integration applied. Right. Yes, 2 correct. Is only in case of pipe. If it is parallel plates, you will prove the 1.5. So only for pipe flow, only for laminar pipe flow, only laminar pipe flow. Flow is ideal. V max, V mean same. Rectangle shape. In ideal flow, in viscous fluid, non-viscous fluid, in non-viscous ideal flow, V max by V bar is V mean is equal to 1. So rectangle shape, na? So answer is 2. Ratio of the maximum velocity to mean velocity in laminar flow. Turbulent flow different. Ideal flow 1, laminar flow pipe 2, laminar parallel plates 1.5, turbulent plate 1.2. We'll come into that picture in case of turbulent. Okay, excellent. Another one more question. In fully developed laminar flow in a circular pipe, the head loss due to friction is directly proportional to dash 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 mean velocity or square velocity. Yes, interesting. In laminar pipe flow, the head loss nothing but Huygens loss. Head loss in laminar pipe flow or Huygens-Poiseuille's loss, one and the same, is equal to HCl. L stands for loss, laminar, is equal to proved one, F L V square by 2GD. F is replaced by 64 by RE into by cancellation of all these properly, number 2, 64, 32, mu, V, V square V cancel, na? Proper cancellations, okay. So, this V times cancel, right? This 2, 32 times cancel, right? Like that. 32 mu VL by rho G D square. This is proved, right? 32 mu VL by rho G D square. Units meters of fluid, meters of water, meters of oil, meters of anything. Now, if you see closely, keeping other parameters constant, HL directly proportional to V. In the laminar only, not in the turbulent V square. So, mean velocity, right? Correct. Square wrong. Mean velocity correct. Right? Head loss is directly proportional to V. Proved one this. Very clear. It's only for laminar, only in laminar. Valid only in laminar. Only in laminar pipe flow. 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 If it is turbulent flow, HL is proportional to V square. Yes, answer mean velocity correct. (1988). Discharge in meter cube per second for laminar flow through a pipe of diameter 0.04 meter, 40 mm, having a centerline velocity, yes, having a centerline velocity 1.5 meter per second. Yes, in general, discharge is equal to cross section or normal area flow perpendicular area, flow direction perpendicular area into mean velocity. If it is radial flow, radial velocity suppose, then radial area 2 pi r into dr type. Here integration normal na 0 to r, so pi r square. Yes. If you simplify this, this is A, this is V bar is equal to Q. Flow through pipe na, flow through pipe. In this direction, flow. If you see in this direction, the view is circular view, right? So, Q is equal to pi by 4 d square or pi r square into average velocity, nothing but mean velocity. He has given center line velocity. Center line velocity is maximum. Center line velocity in the laminar flow maximum. In any flow maximum. This is V center line, which is maximum. Here we mean at certain distance R bar. R bar is equal to capital R by root 2. This also we have discussed in 1 mark, right? Now, average velocity, we'll take the another step, or here only. V bar is mean or average. Mean or average velocity in laminar flow, laminar pipe flow is equal to 0.5 times center line velocity. Center line velocity is also called maximum velocity. Now substitute that. Q is equal to A into V bar is equal to A into V max by 2. Q is equal to pi by 4 d square into V max is given, that is V center line by 2. Pi by 4 0.04 whole square into 1.5 by 2. Units meter square, meter per second. The final unit meter square into meter cube per second. Simplification, this simplification pi by 4 into 4 by 100 into 4 by 100. 0.04 means 4 by 100 whole square into 0.75. 0.75 means 75 by 100. 1.5 by 2 is equal to 0.75 is equal to 75 by 100. This is simplification, right? Now, by cancelling some terminology, right? This 4 cancel. This 4 here 25 times. 25 here 3 times. The quantity 3 pi by 10,000 meter cube per second. 3 pi by 10,000 meter cube per second. 3 pi by 10,000 meter cube per second. Yes, correct. Answer D, correct. If it is mean velocity, no velocity indicated in exam, take it granted as mean velocity only. Unless otherwise stated, the given velocity is treated or considered or assumed to be mean velocity. D answer correct. Otherwise C answer it could be. If it is given mean velocity, right? Now D correct. Next question. Fluid is flowing with an average velocity. If not given, also taken as average only, mean only, because given clearly. Fluid is flowing with an average velocity of V through a pipe diameter D over a length of L. The head loss is given by FLV square by 2GD. This is called Darcy's-Wilbosch equation applicable to pipe flow. F is called friction factor. Friction factor depend upon Reynolds number. The friction factor F for laminar flow in terms of Reynolds number. F you want to replace, right? So, In case of laminar flow, let us see here solution. In case of laminar pipe flow, the head loss nothing but Hagen-Poiseuille's loss. The head loss is equal to 32. Is all derived one. We have done these derivations, right? 32 mu V L divided by rho G d square. Now according to, this is one, right? This is first point. Second point, according to Darcy's equation, Darcy's equation for head loss in pipe flow is given by F L V square by 2 G D. This is equation 2. If we equate these two equations, one is Darcy's equation for head loss in pipe flow, that is equal to, in particular laminar pipe flow, Huygens equation, 2 is equal to 1. F L V square divided by 2 G D is equal to 32 mu V L by rho G d square. Proper simplification, right? G cancel, D cancel, L cancel, V cancel. Now write the balance terminology. By writing balance terminology, F into V by 2 is equal to 32 mu divided by rho D. F is equal to cross multiply 64 mu, right, divided by 32 mu, that's it, divided by rho V D. Further simplification, 64 divided by rho V D by mu. 64 divided by rho V D by mu or V D by nu. Rho V D by mu or V D by nu, that is Reynolds number, is equal to 64 by Reynolds number. Friction factor in laminar flow, friction factor in laminar pipe flow in terms of Reynolds number only. Friction factor is not dependent on the pipe roughness, independent upon the type of the pipe surface, just a function of Reynolds number. Reynolds number is function of physical property, diameter, flow property, velocity, and fluid property, kinematic viscosity. That's it. Purely, friction factor is purely function of physical property, diameter, flow property, velocity, fluid property, viscosity, kinematic viscosity. That's it. So by taking this, friction factor in laminar pipe flow, friction factor in laminar pipe flow is equal to 64 by Re. 64 by RE. Yes. So here friction factor for laminar flow 64 by RE, correct answer. You have to fill the blank. 64 by RE. 64 by RE, answer correct. A 2 marks question those days, 1994. Now familiar over a period of time, these questions become easy. When question twisted, then strain for the student community. Right. Yes. Next question. For a laminar flow through a long pipe, the pressure drop per unit length increases. First laminar flow, that too type of the system is pipe. Okay. So head loss, pressure drop. Pressure drop in laminar pipe flow delta P is equal to 32 mu V L by D square. Delta P is equal to rho G HL na. In laminar flow, HL is equal to 32 mu V L by rho G D square. So rho G cancelled. Rho G cancelled. 32 mu V L by D square, correct. This is the pressure drop. Pressure drop per unit length. Therefore, pressure drop per unit length in laminar flow is equal to 32 divided by mu into V multiply divided by D square. Simply delta P by L. Pressure drop per unit length. Pressure drop per unit length. 32 mu V L by D square. Now, he is asking in terms of cross-section area, diameter of the pipe, cross-section area. So, pressure drop per unit length is directly proportional to 1 by D square, inversely proportional to D square. If it is multiplied with pi by 4, it become area. Okay. Now, with this, what is the statement? This is wrong, na? Check it, B statement. Pressure drop per unit length inversely proportional to square of the dia, not proportion. Proportional to 1 by diameter. Proportional to diameter is wrong. Proportional to diameter of the pipe. Proportional to 1 by diameter, 1 by square of the diameter, inversely proportional, otherwise square of the diameter, right? Next, this is, so B wrong. Next, inversely proportional. So this can be converted delta P by L proportional to, okay. Now, here pi by 4, otherwise you can simplify that way also, is equal to 32 mu V by D square. My intention is 32 mu V multiply pi by 4 divided by pi by 4 D square. Delta P by L is equal to 32 mu V pi by 4 divided by, what is the pi by 4 D square? Area, cross section area. This is cross section area of pipe. So, keeping in mind this, 8 pi, 4 times na this 8 times na, 8 pi mu V by cross section area. Right. Right. So by taking this into consideration, drop in pressure per unit length is equal to 8 pi mu V divided by cross section area, proportional to dynamic viscosity, proportional to 1th or velocity of the flow, inversely proportional to area. Identify the option. Inversely proportional to square of the cross section area. Yes, wrong. Not square, square of the diameter. Okay, cross section wrong. Inversely proportional cross section area. C correct. Linear proportion wrong. So C answer perfectly matching. Change of pressure, drop in pressure per unit length of the pipe directly proportional to 1 by A. Nothing but inversely proportion, right? So answer C correct. See, the time is a factor there. If you analyze like this step by step, you will get into that. For the given pressure drop, relation between viscosity, velocity, more the viscosity, less the velocity. Less the viscosity, more the velocity, inversely proportion, keeping delta P. In place of this V, you can replace discharge also. V is equal to Q by A. For the given pressure drop, viscosity inversely proportional to discharge. Like that questions can be formed. Parameters which determine friction factor for turbulent flow. Yes, very turbulent flow. In turbulent flow, right, in that too rough pipe. So that means Reynolds number less than 2000 laminar pipe, independent upon the pipe roughness. In laminar flow, friction factor no way connected to pipe roughness, just depend upon RE only. In case of smooth turbulent flow, friction factor is function of RE but different formula, inversely proportional to RE to the power of 1 by 4. In case of rough turbulent flow, friction factor is a function of Reynolds number as well, pipe roughness. If Reynolds number is too high, more than 10 to the power of 7, is only function of pipe roughness. Right? Proud number, it is irrelevant for us. It is the gravity force and open channel flows. Mach number is compressible flow. So very clear, elimination method also, Reynolds number and relative roughness. So 1 by root of Nikod's equation is equal to 2 times log base 10 radius by roughness plus 1.74 or 73. So R is a radius or diameter by 2 and K. So friction factor is function of, otherwise you can take this way also. Friction factor less than 1 lakh, more than 4000, then this is like this. R to the power of 1 by 4. Right. So answer is C. Answer is C. Now from the given statements, so wrong statements this. Assumption, this is approximate answer. Question supposed to be parallel mixing that pipe surface is 0. That was question in the gate civil. Now here given the distance perpendicular to mean flow. Where is mean flow? This is the mean velocity. Suppose this is maximum velocity. Suppose somewhere mean velocity, right? So mean flow covered by the mixing particles. Here I told you mixing particles are covered. So approximate answer A only correct. Okay. Next question. Oil flow through a 200 mm diameter horizontal cast iron pipe. Friction factor this much. Of length 500 meters. The volumetric flow rate is this much. Head loss due to friction. Okay. Yes. Head loss in a pipe. Head loss in a pipe flow is equal to F into L into V square by 2GD. Here replace V. F into L into Q by A whole square by 2GD. The simplification by taking G 9.81 pi by 4 D square, FLQ square by 12.1 d to the power of 5. FLQ square by 12.1 d to the power of 5. By substituting these values, head loss due to friction is equal to F L Q square divided by 12.1 d to the power of 5. Friction factor (0.0225). Length of the pipe is 500 meters. Discharge square 0.2. 12.1 d to the power of 5. 0.2. By simplification, this one one six 116.22 metric meters. This is head loss. Check the options given. 116 correct. Answer A. So clear question. 116 meters. Right. We got 116.2. You got 1.18, right? Because here 12.1, it's a 12.09. So round up 12.1. Right. In case of turbulent flow of a fluid through a circular tube, nothing but pipe, compared to the case of laminar flow for the same flow rate, Q turbulent is equal to Q laminar. The maximum velocity is comparison of the center line velocity in case of laminar turbulent. Then shear stress at the wall in case of turbulent and laminar, and the pressure drop across the given length. Pressure drop across the given length. Comparison turbulent and laminar pipe flow. The correct words for the blanks. Fill in the blanks type, right? Now first let us see turbulent laminar with respect to maximum velocity, right? That is same flow, maximum velocity, right? In laminar pipe flow, in laminar pipe flow, V max is equal to 2 times mean velocity, because it is parabolic velocity profile. In turbulent pipe flow, V max is equal to V mean into 1 plus 1.43 root F. Generally, F is eligible answer, eligible value 0.018 or 2 like that. So, V max approximately you will get 1.2 to 1.25 V mean. It is 2 rupees, just fun type. It is 1 rupee 20 paisa to 1 rupee 25 paisa. So, with this observation, what happens? V max turbulent for the same discharge, for the same mean velocity, less than V max laminar. This is correct. So, maximum velocity means center line velocity, axial velocity of the pipe for the same discharge, nothing but same cross section area, same velocity. Vmax turbulent is 1.2, 1.2 to 1.23 like that of the mean, whereas laminar pipe flow Vmax is 2 times now. So, this statement is clear. So, lower. So, this is wrong, right? Here na, this is 1. So, this is correct. C or D possibility. Now, second step, wall shear stress. Wall shear stress for the turbulent flow compared to laminar flow. So, shear stress discussion, right? Shear stress laminar is equal to Newtonian fluid type, right? Dynamic viscosity into velocity gradient. Shear stress turbulent definitely more than laminar on account of eddy viscosities. So, tau laminar plus eta, this is called turbulent dynamic viscosity eta into, right? So, this way you can write that additional amount this is additional amount of shear stress of turbulent. This is mu times du by dy plus eta times du by dy. Mu is coefficient of viscosity, dynamic viscosity, absolute viscosity, whereas eta is the viscosity due to turbulency, little bit more, some fraction amount. So, with this observation, shear stress in turbulent flow greater than shear stress in laminar, confirmed. The conclusion is this. Shear stress turbulent greater than shear stress laminar. Shear stress at the wall, the maximum shear stress at the wall in turbulent flow higher than the shear stress in the laminar. See, higher and higher. Still not clear answer. Still not decided C or D. So, this is lower here. This is higher here. This is first discussion. Now, we will move to another area, that is comparison. Pressure drop across given length. Comparison turbulent with laminar. Right. Third, pressure drop in laminar pipe flow. pressure drop in a laminar pipe flow is equal to 32 mu V L by rho G will cancel because of the head case, it will be there. Rho G will not be there, right? D square. That means pressure drop is proportional to velocity, right? In case of, this can be written as F L V square by 2GD, where F is 64 by RE. By replacing friction factor, we will get the 32 mu VL by D square. So, keeping all parameters same, proportional to V. In case of turbulent pipe flow, F L V square by 2GD. F will be given according to the Reynolds number, range, and pipe friction roughness also. Even though F slightly difference in the laminar turbulent, right? But velocity square, na? Pressure drop is proportional to V square. Proportional to V square. Proportional to V square. Proportional to V square. So, proportional to velocity, proportional to V square. Which means that pressure drop in turbulent is more than pressure drop in laminar. Pressure drop in turbulent greater than pressure drop in laminar. So, with this conclusion, third fill in the blank can be filled higher. Here higher, third point. So, option C is concluded. A good question this. Option C is concluded now. A streamline body is defined as a body about which flow is laminar. No, flow can be transition. Flow can be, say, turbulent. This is wrong. Flow is along streamlines. Flow over the curved surface, streamline can be curved. One tangent line, one normal line. May not be this. Certain extent applicable. Let us see further. Drag force 0. Drag force never be 0. Certain amount will be there. The flow separation may be suppressed. The first priority C, second priority B, third priority D. Drag force is equal to dynamic pressure into drag force is equal to dynamic pressure into area of rho V square into A, rho A V square. This is called theoretical drag force. Actual drag force is equal to coefficient of drag into half into rho into A into V square. V is streamline velocity. So, streamline body is one in which drag forces may be minimum, not exactly equal to 0. That means velocity 0. No. Where there is a relative velocity means relative velocities. Velocity of the viscous fluid and velocity of the moving body. Velocity of the moving body may be 0, but velocity of the moving fluid will be there. Sometime body moving in the stationary fluid. So this will be relative velocity. Recent literatures not much focused on the drag forces. Forces on submerged bodies we have syllabus. Force hydrostatic on submerged body surfaces we have hydrostatic force. This is called hydrodynamic force. So hydrodynamic force, the velocity is relative. The fluid moving in this direction, body moving in this direction. This velocity plus this velocity. Both are moving same direction. Difference in velocity. Like that, relative velocity shall be taken for calculations of the dynamic pressure force. By multiplying CD, you get the actual pressure force. That is called drag force. So out of 4 options, very best option is flow separation can be suppressed. Answer C is suitable. Flow is along the streamlines. Mostly preferred to reduce the drag, but need not be 100% statement committed for that. Flow along the streamlines. Flow parallel to the surface. Right. Streamlines can be curved. Streamlines can be lines. Curves means we'll have 2 lines. Tangent line, normal line, components, velocities and accelerations. So C is preferable. Suppose this is the body. A streamline body. Right? This is the flow. Right? Like this. These are the streamlines. This is the wake. This is the drag force. This is the lift force. This is the resultant force. This is the angle made by the resultant with reference to horizontal. This concept we have discussed. So people attracted to answer, oh, streamline body is the body in which streamlines are parallel. So need not be. Right. Parallel lines and curved lines, both possible in streamboard. Another question. Predominant forces acting on an element of the fluid in the boundary layer over a flat plate in uniform parallel streamlines. Yes, interesting. This is the flat plate. This is the free stream velocity. This is the boundary layer. Boundary layer thickness increasing in the direction. This is the x direction, right? If you take a small element, real fluid element, viscous fluid element, there are 2 forces. One is viscous force, second is inertia force, right? Viscous force, inertia forces are correct. Within the boundary layer, over a flat plate, there are 2 forces predominant. Force 1 is inertia force, mass into acceleration. Inertia force is equal to mass into acceleration. Viscous force is equal to shear stress into area. These 2 forces are considered. Suppose a question can be possible in future. Flow is ideal. What about boundary layer thickness? Not possible. 0. No boundary thickness. For ideal flow, boundary layer thickness is 0. In case of real fluids, which means viscous fluids, boundary layer may be 0 at leading edge. That's it. It keep on increasing depending upon the type of boundary. Boundary layer can be laminar, boundary layer can be transitional, boundary layer can be turbulent. Depend upon the type of boundary, the thickness varies. So present answer, predominant forces in the boundary layer theory over a flat plate are viscous forces and inertia forces. Answer B correct. Necessary and sufficient condition which brings about flow separation. Interesting question. This is the flow over curved surface. Free stream. This is the boundary layer. right? Now, this is the variation of the pressure gradient. Here, dP by dx less than 0. Here, dP by dx greater than 0 or equal to 0. The flow separation here observed. This is the flow separation. The velocity profile is like this. Like this. The velocity profile is like this. Yes. Like this. Velocity profile. Positive pressure gradient means abnormal pressure gradient means adverse pressure gradient. dP by dx positive means adverse pressure gradient. This is called adverse pressure gradient. Adverse pressure gradient. Adverse pressure gradient means flow separation. True. Necessary and sufficient condition which brings about the flow separation in the boundary layer is true. True statement. True. Flow separation is observed over the flat plate? No. Flow over the curved surface, flow separation is observed. Flow over the curved surface, flow separation is observed when pressure gradient is greater than 0. That is called adverse pressure gradient. Adverse pressure gradient. Next, as the transition from laminar to turbulent flow is induced in a cross flow over circular cylinder, the value of the drag coefficient drops. If you take a cylinder, this is the cylinder, flow is taking place like this. Here wake is formed. This is the laminar. In the laminar and turbulent, if you compare, the transition from laminar to turbulent induced in a cross flow perpendicular to the axis, not along the axis, over the cylinder, the drag force coefficient drops. Yes. If you take this into, say this is laminar. If you take another case, same cylinder, the flow like this. Here wake formed, right? So, the flow separation is away from the system. So, in case of laminar to turbulent shifting time, the drag coefficient drops. So, that means if you take a cricket ball, smooth initially, when you take a new ball, when you make it rough over a period of time, continuous playing with the cricket ball with the bat and all, moving on the surface, that become rough. People still do roughing more. The cricket ball more rough. Turbulent flow more appears. More turbulent flow, less coefficient of drag. Less coefficient of drag, then the motion of the ball very difficult to predict. So, the player who bat the ball is difficult to predict. Spin bowl is a complex to play. Like that, making surface rough you can create the rough boundaries, makes the turbulent flow. Turbulent makes the reduce the coefficient of drag, thereby reduce the drag forces. So making the flow turbulent in such cases advantage, reduce the drag forces by reducing the coefficient of drag. Answer true, correct. Yes. One more question. Right. In terms of speed of rotation, in terms of speed of rotation, speed of rotation of the impeller. Here word impeller. Impeller means pump, centrifugal pump, centrifugal pump, plunger or piston, reciprocating pump. Speed of rotation of the impeller, nothing but pump N, RPM, discharge Q, and change in the head H through the machine. Then what is specific speed of the pump? Interesting question. Specific speed of a pump different, turbine different. Pump means rotating element, turbo element, turbo machinery element is impeller. In case of same question, impeller is replaced by rotor, producing power P using discharge Q. That becomes specific speed of a turbine. Because of impeller, the question becomes specific speed of a pump. This is the question. Specific speed of a pump is equal to N under root Q divided by head developed to the power of 5/4. Pump impeller. Impeller is rotating element of the pump whose specific speed is like this, which delivered discharge Q at particular RPM N against the head H. A homogeneous fluid machinery which rotates at N, delivered Q meter cube per second against the head H. If it is turbine, in case future, then it become the rotor, runner. Rotor or runner is equal to N under root P. P is the shaft power developed by the turbine. It's to the power of 5/4. So see the difference word, impeller, rotor or runner, just makes the answer different. So this is the way we need to have information about the turbo machinery specific speed, right? So answer is here, NS impeller, NS pump, same meaning, N under root Q divided by, fill in the blank, H to the power of 3/4, N in RPM, Q in meter cube per second, H in meters. One more question, 1994. Kaplan turbine is A. So and so options, so and so options. We know already summarized. Pelton wheel is a high head low discharge, low specific speed, then tangential flow and impulse type. So every turbine has its own features. Here Kaplan turbine, right? So Kaplan means propeller type. The features, low head, high volumetric flow rate, high discharge, high specific speed, axial flow. These are the features, axial flow, axial inward flow, and reaction type. Reaction type. So let us see how it can be. I head mixed flow, no. Mixed flow is there, that is a modern Francis turbine, but a medium head that. Low head axial flow, low head axial flow, Yes. Inward reaction turbine, not outward. Impulse inward. This is called Pelton wheel. Remaining not attaching. Outward is the reaction turbine, Fennery reaction turbine, Fennery type, which is not in the use much. So present is low head axial flow, correct. Kaplan turbine is low head, high discharge, high specific speed, axial flow and reaction turbine. So low head axial, right? Low head axial, low head match, axial match. Remaining other 3 features are there. Total 5 features each one. With this, what we understand now, if we say Pelton wheel features high head, low discharge, low specific speed, tangential flow, then impulse type. These are the 5 features for the Pelton wheel. As we discussed Kaplan turbine already, low head, high discharge, axial flow, high specific speed and reaction type. Here reverse. High head, low discharge, tangential flow, low specific speed, right? And low discharge, high head, low specific speed and impulse type. Similarly, if you take Francis turbine, then medium head, medium discharge, medium specific speed, radial inward flow and reaction type. Next question. Okay. At present, this question answer is B. Kaplan turbine is a propeller turbine whose requirements are low heads, high discharges, high specific speeds, reaction type and axial flow. 2 mark questions. Cavitation in a hydraulic reaction turbine is most likely to occur. Reaction turbines cavitation definitely occurs, not in Pelton wheel. Reaction turbines, Francis turbine, Kaplan turbine. The low pressure zone, exit of the runner wheel, exit of the rotor or inlet of the draft tube. Exit of the rotor or inlet of the draft tube, right? So here likely to occurs at cavitation hydraulic reaction turbine is most likely to occurs at entry, no. Exit means out of the draft tube, no. Stator exit, no. Rotor exit, correct. Rotor exit, outlet of the rotor, nothing but inlet of the draft tube. Inlet of the draft. Answer D. Next question. Specific speed of a Kaplan turbine. See, this comes under multi-jet Pelton wheel. Multi-jet Pelton wheel, 30 to 60. Less than 30, single jet Pelton wheel. Single jet Pelton wheel. NS is less than 30. 30 to 300, Francis turbine. 300 to 600, Kaplan turbine. Answer C. 300 to 600 range valid for the Kaplan turbine. 60 to 300 for the Francis turbine, 60 to 30 to 60 multi-jet, less than 30 single jet Pelton wheel, right? So, this is one additional point. So, if you more than 600, can you propeller turbine? Any other, say, reaction turbine, right? Correct answer is C. So, you can make out a list. NS less than 30, Pelton wheel with single jet, right? NS less than 60, more than 30. This is Pelton wheel with multi-jets. NS more than 60, less than 300, right? This is Francis water turbine. NS more than 300, less than 600, Kaplan. So, for more than this, you can say propeller turbine. Then what is difference between propeller turbine and Kaplan turbine? Kaplan turbine consists adjustable rotor blades. Propeller turbine consists fixed blades, rotor fixed blades. This is the difference. That means this is the shaft, vertical. This is the rotor. These are the rotor vanes. These rotor vanes are adjustable in case of Kaplan. In case of propeller, these are fixed.